So I'd like to thank the organizers for inviting me. I'll talk about some topological aspects of concurrency theory. So we'll have some high-dimensional objects here, and perhaps I'm a little combinatoric, so I hope it fits somehow, at least nominally, with the topic of the conference. Okay, so this is joint work with Martin Rausen from Denmark. Now, concurrency theory deals with systems in which several computations are running or executing simultaneously and possibly sharing or interacting with each other. And the main issue here is how to devise a schedule for the computations so that on one hand all computations will have the required resources that they need. On the other hand, you want to optimize something, say the length of the computation, and actually maybe some other complexity measure of the computation, so how complicated is the computation. Now, there are several models for mathematical models for concurrency, and we'll focus on one very simple one due to Dijkstra invented by him in the 60s. And this model has some topological content or geometrical content, and gives rise to things called path spaces, which are topological spaces, which somehow parameterize the possible executions of the program. And we'll be interested in the topological characteristic of these spaces. So these spaces are like moduli spaces for concurrent computation. So the plan is as follows. I'll first recall or tell you about the Dijkstra PV model. And this is a very simple model, and we'll discuss both the combinatorics and the path spaces that arise from this model and see a few examples. Then we'll focus on path spaces of specific programs which are called instantaneous, simpler than the general model. And in that case, we can actually write the homotopy type, or rather the Poincare series of the path spaces, in terms of the combinatoric of the model. And finally, we'll see some applications to some previously known and some previously unknown things. Okay, so what is a Dijkstra PV model? First, it has resources. So the resource set is just a finite set representing some resource, say nodes in a distributed computer system or something like a memory site. And each resource has a capacity. The capacity is an integer that indicates how many processes can use it simultaneously. Now, what is a process? A process is simply a sequence of accessing and releasing a particular resource. So the PA denotes accessing or locking the resource, and VA denotes the unlocking of the resource. And I've asked some Dutch guy what is P and V, and he said that he doesn't know, but certainly doesn't relate to accessing and releasing, but that's okay. But it's something in Dutch. Now, what is a process? Here is an example of a process. We have three resources, A, B, and C, and we lock A, lock B, release A, lock C, release C, and release B. And of course, in this case, each resource was used twice, but you can use it again and again, and that's actually the source of complexity.
Where's the value of P of A and B? Where do they live?
No, this is just an indication. P says that, yes, we open A, and V means that we close A. Yeah, this It's a very simple.
I'm using A now, and I no longer use it. That's the
Yeah.
It's like in the bathroom you have occupied, not occupied.
Yeah. Okay. That may be also very useful.
But can you have several?
Yeah.
Unlike the
Yeah.
bathroom, yes.
Yeah, you can. Yeah, this may be a little embarrassing, but you can have. Okay, so this is the static information. And now, what is a PV program? Well, a PV program is simply an n-tuple of processes that have to live together. So an execution of this n-tuple is a time schedule for carrying out all the actions in such that two things hold. First of all, we have to respect the order of accessing and releasing the resources in each process. And second of all, the capacity constraints must hold. So we cannot use at a specific point in time, we cannot use a resource more than its capacity allows us. So here is an example. We'll have two resources, A and B, with capacities 1, both of them. And we have two processes. The first is open A, open B, close A, and open B, open A, close A, and close B. So here is a legal execution, a timeline for legal execution. First process opens A, opens B, closes B. Second process opens B. First process closes A, and then second process opens A, closes A, and closes B. So this is okay because every resource is used at a certain point in time. If we look, say, at this point in time, then B is used but by process 2, but not by process 1. On the other hand, this is an execution which is illegal because at this point in time, B is used both by process T1 and 2. Okay. Now we would like to see the geometrical content of this model. So we would like to encode the dynamics somehow topologically. And this is also quite simple, but prior to that we have to talk about path spaces. So what are path spaces? Suppose that we have some set in Rn, and we look at 2 points in the closure of X, say y0 and y1, and we assume that y0 is less than y1 component-wise. A directed path in X is just a continuous map from the interval 0, 1 to X, such that each of the pi's is non-decreasing. So just something like that. Goes from this point to this point. And the path space of X from y0 to y1 consists of all directed paths from y0 to y1. So, for example, such a path or a path that goes on the axis and so on. And the topology is just the natural topology. 2 paths are closed if at each point in time they are closed. And then you get a topological space. It's an infinite dimensional topological space. So as if you want to talk about the, say, homeomorphism type, then this is not realistic. But it turns out that these spaces have have a topology of a finite complex. So for example, let's say remove from R3 the point 1, 1, 1, then Px between the origin 0, 0, 0 to 2, 2, 2 is a homotopy equivalent to the circle. So let's see why this is true. Each point in this circle, gives us a path from 0 to 2 by first walking directly in a straight line to that point, and then continue from that point to 2 to 2. And you can intuitively, I think it's clear that you can somehow push any non-decreasing path. You can push it in a coherent way, so that these two spaces are really homotopy equivalent. Okay. Now we will want to associate a path space with a PV program, and this will do as follows. The formal way is also quite simple. Suppose that we have a process, so opening and closing various resources. Then we can think of the process. If we take k to be the total number of operations, we can think of it as a partition of 1 to k into pairs, where each pair, the first integer indicates the opening time, the second integer indicates the closing time. So, for example, in this process gives us this partition. So 1, 3 is the opening and closing of A, and so 4, 5 is the opening and closing of C, so on. And we label each pair by the resource that is being used in this interval.
William, sorry, I just want to show you're assuming that each individual processor makes reasonable requests, right? I cannot ask to first close, or can I do this?
You cannot ask to go out of the bathroom before you went in. Yes.
Okay. No,
yeah.
I can assume that I'm closing for somebody else. It's not completely, but anyway.
Yeah.
We are assuming that each individual, if we run one of them, it would be okay.
Yeah, it will be you can think of it as a partition, just a partition, and you.
In all your examples, it was just each one was accessed once.
Right, but this is definitely not the case. Actually, the interesting thing is that when you use it again and again at various points, and we'll see that. Okay, now once we have this partition, we look at the PV program, so T1 to Tn, and say Ti has length Ki, and we look at the space of legal executions. So what is the space of legal executions? We define the multiplicity of a point in time to be, if the point in time is x1 to xn, we define the multiplicity to be the number of i's, such that with respect to some resource A, the number of i's that use resource A at the point xi. Okay, so formally you look at all i's such that xi belongs to PV, and the label of PV is A. Okay, once we have the notion of multiplicity, we can define the allowed zone. So the allowed zone for this PV program is Rn minus all points for which the multiplicity at some point is bigger than the capacity. Okay, and so using the notation of the previous slide, Pxt from 0 to k plus 1 is just the space of legal execution of Tk, and this is our object of interest. So we are interested in this topological space. Yes, so okay, so let me jump ahead a little bit and say that we will have a path which will describe where in the program I we are in. So Pix will tell us how I runs its business. So what we want is that at time x, which is x1 to xn, each of the processes have its own time. Yeah, it can run its own time. So we want that at time xi, we look at time xi and ask, what resource do we use? So if we use A, we record it. And what we want is that for a point will be legal, we can pass through this point if this point is contained in or if the number of i's for which xi is contained in an interval that uses A is bounded by k of A. We'll see an example. This is maybe clarify the things. Okay, so this is our character. Yeah. Okay, here is a very simple example. Actually, this tells the whole story in terms of the terminology. Suppose that we have these T1 is PA, PB, VB, VA, and T2 as before PB, PA, VA, and VB. And the capacities are 1. We are not allowed to use a resource by more than one process. So I claim that this is the forbidden zone. Because why is, say, this point forbidden? Because this point lies between PA and VA for process 2, and lies also between PA and VA for process 1. So we just, it's disallowed. And so on. And so we get this Swiss flag. And here the trace space, well, we are allowed to go either on the right or on the left. And the trace space is very simple. It's just homotopy equivalent to S0. Just two things. Yeah, two things that you can do. Okay. Now.
So wait, I have a question.
Yeah.
So this seems to be a very discrete thing. Right? So there's no. So why do we review it continuously? I mean, there's no difference in these two different points. They are both between PA and PB for the first one, and between the PB and P for the second one. They're all equivalent to each other. Each one of these squares are basically equivalent.
Yeah, in this
you could represent it on a grid rather than on a continuous square.
Yeah, that's correct. I mean, but yeah, but you cannot go through here, right? I mean, this is. Yeah, you can represent. It's a discrete. It's a topological space that can be described discretely. Yeah, but okay, but there are several things that should be okay. So. Concurrency theory is so I'm told, a very applied branch of computer science. It has also theory, but also people actually try to devise algorithm for concurrency. And one can ask reasonably, why is the topology of this space relevant? Okay, so a good question. So I'm preempting if there is some. So one thing is this is agreed among even the die-hard applied concurrency practitioners is that the number of connected components is important because if two things use the same, if two paths are in the same connected components, then concurrency theories think of the results as the same, the result of the computation. Now, it's a more delicate question whether higher homotopy is relevant. But then again, at least Martin found some guys who actually claim that this is important because we want to know eventually whether two concurrent settings are equivalent in some sense. And it can be argued that the criteria can involve some natural pairing between the path spaces. So, for example, homotopy equivalence or isomorphism in homology and so on. Okay, so this is for the apology part. Now, one can ask what kind of spaces do we get? Because so far we have seen very simple things like, two discrete points and circle. Now, there is an algorithm, a simple algorithm due to Martin Rausen, which tells us that, in fact, the homotopy type that we get is of a finite complex. And And here is Martin's way of seeing it. So take this square and take its shadow on both axes. So either here or here. Okay, and the same for this square. And look at the four possibilities. Then, on a quick reflection shows that if you look at the path space of each of these guys, it's actually trivial homotopically. So there is essentially only one way of going from here to here. Yeah, you may have to. So in this case, you go here or 0, right? Okay. So you look at all these four possibilities, or in general, as many possibilities as you need, and what you get is, in fact, a good cover. So you get a bunch of spaces that are all contractible, such that the intersection of any of them is also contractible or empty. And then, by the nerve theorem, the nerve lemma, you infer that the path space is actually homotopy equivalent to the nerve, and at least you get a finite complex. In this case, you get 3 non-empty contractible sets, such that the intersection of any of them is empty, actually. There is no intersection between this and this. If you want to take a path which is okay in this respect and in this respect, then there is no such path. So altogether here you get S0 wedge, just wedge S0, so which is 3 points. Okay, so we are convinced that we get something which is homotopically a finite complex, but in fact you can get any complex. So any homotopy type you can get. As complicated as you want, you can devise some PV program that will recover such a thing. Okay. Okay, so this is for the introduction. Now we'll talk about some specific type of PV programs that they look kind of simple, but in fact they give rise to interesting path spaces that have been considered quite widely in the literature. And we say that the program is instantaneous if all the access and release times are occur at the same time, so occur just consequently. So for example, Ti can be PA1, VA1, so to PAK, VAK. Now in that case, replacing PA, VA by a point would not change the homotopy type of the path space. So for example, this kind of obstructions are encoded by PA, VA, PB, VB, and PB, VB, PA, VA, like this. And you can replace them by these 2 points. And
how does a machine know that it might do something illegal if you don't know what the other person's doing at the exact same time? So you only see after the result.
So I'm not sure. I think they have some kind of so it's something that perhaps runs a lot of time. So you decide ahead of time what is the best. But I'm not. Yeah.
But in your definition, in terms of what's illegal, you see immediately afterwards if it's illegal.
It's a request that you cannot serve. You know?
Okay.
Yeah, you perhaps get stuck, but I'm not sure. They have a lab in Paris that actually runs these things, and they even compute by computer. They try to compute the homotopy of path spaces, but since but it doesn't run very well because you can actually recover any homotopy type. So it's so it gets stuck. Okay. But here we'll see that for this type of restricted models, we can actually give a kind of formula. And this is the main thing. So let's start with an example. suppose that we take these very simple programs. Each TI is a sequence of PA, VAs, and we have just one resource. So you access and release immediately the same resource KI times, but the capacity is n minus 1. So you are not allowed, of course, not everybody is allowed to use the same resource. Everybody but one is allowed. In that case, a little thought shows that actually the allowed space or the abstractions are just this product of discrete sets. So you remove from Rn this part of the lattice. You can think of it as Zn. You remove Zn, the lattice, and the question is, what is the path space? So if we are in 2 dimensions, which we'll see in a minute, then there are only discrete points, and the number of discrete points is just k1 plus k2, choose k1. Let's see the example. If we remove this lattice point, well, we can decide at each point whether we go up or to the right, and the number of choices is just 4 plus 3, choose 4. When you're in dimension at least 3, then the situation is less clear. But Rausen and Ziemiański computed that Ziemiański computed that you get homology only in dimensions which are multiples of n minus 2 and non-zero multiples, and you get this huge homology. Let's see an example of this. So here I just remove this cube, the points, the vertices of the cube. The lines here are just ignore them. I just drew them so that we'll recognize that it's a cube. Now this has 8 one cycles, which are similar to the example that I showed at the very beginning, but it has also one cycle in dimension 2. So beta 1 is 2, beta 2 is 1, yeah? And here is the cycle, the 2 cycle that is part of the path space. You draw a small circle around this point, a small circle around this point, and you look at all the paths that connect 0 to a point on this circle, then go to the other circle, and then go to 3, 3, 3. Now, obviously, this is equivalent to just S1 cross S1, which is the torus. So what we get is we parameterize a set of passes by the torus, and it turns out that this is actually a bona fide 2 cycle, and yeah, okay. So this is the example, and now we would like to look at the general case. The general case of instantaneous programs. Okay, so for the general case, we look at just a hypergraph which is inside 0, 1 to the n. So a hypergraph on n. So just a family of subsets of 1 to n. We assume that it's upward closed. It doesn't really matter, but it's clear that it will be clear that we only need filters here, and we look at for each f in f, we remove from Rn all points which have integers in the indices that are prescribed by f. So, for example, if the hypergraph contains the set 1, 2, then we remove all points that have integers in place 1 and 2. So this is the pattern space, or the allowed space of f, and the path space is the path space of this space. So, for example, in the Rausen-Ziemienski case, we just have this hypergraph. The hypergraph is just one set, the set 1 to n. And then we remove just Zn, and the homology was computed by them. And in general, we compute this for general hypergraphs in terms of some combinatorial parameters of f. Okay, so it has several ingredients. So let me make a small detour into topological combinatorics or combinatorial topology. Suppose that we have a partially ordered set, then there is the order complex of P. Its vertex set is just the points of P, and the simplices are ascending chains.
Can you get to what you are trying to prove?
I'm sorry? Okay, so I'll give a formula for this. But the formula has some ingredients which are homology of posets. So these are posets, and these are order complexes. Most of our posets will be lattices and even geometric lattices. So a lattice is just a poset where any 2 points have an upper bound, the least smallest upper bound, and the largest lower bound. And these are particularly nice, at least topologically, posets. They're even nicer when they are geometric. So in geometric lattices, rank of x plus rank of y is at least rank of x wedge y plus rank of x join y. So this can be, say, the lattice of subspaces. That is a geometric lattice. And one important property of geometric lattices is that they have homology only in the top dimension, which is rank L minus 2. This is a result of Folkman from the 60s. Here is an example of a lattice, a geometric lattice. This is the partition lattice of the numbers from 1 to n. So you take all partitions and you order them by refinement. So, and then we get only homology in dimension n minus 3, as Folkman theorem predicts. And this is the Betti number, relevant Betti number. There is also the S-equal lattice, which is a sublattice of the partition lattice. Here you use sets which are either of size 1 or of size at least S. Now, this lattice came up in the work of Lovas and Yao and Bjorner on some lower bound computing problem, and Bjorner and Welker compute the homology directly. This is not a geometric lattice, and they get this formula, which is, well, it's a little bit hard to parse, but what's important is that you can actually compute the numbers exactly. Okay, so let's keep this in mind. We will also need order complexes of matchings. So suppose that we have this hypergraph, and a matching is just sub-hypergraph, sub collection of sets such that they are pairwise disjoint. And let M of f denote the set of all non-empty matchings of f. Again, we can partially order them by refinement. So one matching is less than another matching if every set of the first matching is contained in some set of the second matching. And given a hypergraph and a set in the hypergraph, we can look at all the matchings of f such that each such set is contained but not equal to f. Now, the main point in our computation is that you can actually write the homotopy type of the path space in terms of the order complexes delta of MF bounded by F. And okay, this is a horrible slide. Okay, so what you do is there is a parameter which is a function or a label. You label each set in F by some natural number. You construct some graph out of this labeling. Actually, you just take M copies of each set, MF copies of the set F, and you construct a graph where you join two copies F I and F prime I prime if F and F prime intersect, and you look at the number of acyclic orientations of this graph. This number can be computed by substituting -1 at the chromatic number of the graph, chromatic polynomial of the graph. And again, if we look at the very simple hypergraph, which consists only of one edge, which is the 1 to n, then what we get is the complete graph. Tf of m is the complete graph on m vertices, and the number of acyclic orientations is just m factorial. And okay, now given such an m, which is a labeling of the hypergraph, we can define two numbers which appear here, but just think of them as numbers that are determined by the hypergraph. And then using these numbers and these posets, you can write the Poincaré polynomial of the path complex. So the Poincaré polynomial of the path space is just the generating function of the homology of the dimensions of homology of the space. So it's the sum of dimension of h tilde I minus 1 times t to the I, and it turns out that this is exactly this fk. So we get here this number and this number that were defined here or not defined here, and we get the main part is this product of Poincaré polynomial, but of these matching complexes that are dependent only on the hypergraph and on M. Now, one can have an opinion whether this is simple or not simple, but in some cases it can be computed very easily, and I'd like to give one or two examples. Yeah, maybe I think well, if we'll have time, we'll return to it, but I don't think we'll have time. Okay. Let's see one example where this is very simple. So let's go back to the Rausen-Ziemianski case. So if we remove Zn, we have only one set here. Now, since there are no elements, there are no sets which are not the full 1 to n, this means that the order complex is just empty. And therefore, its Poincaré polynomial is just 1. And therefore, you compute by the formulas, you compute that B is the product of Ki choose M, and C is M times n minus 2 plus 1. And then by the general formula, all that remains is exactly this expression, which agrees, of course, with, or luckily, with the previous result. You can also do the same thing Okay, let's me. You can also do the same thing with the Sk equal path space. In this case, every process, as before, Ti calls Ki times the single process of capacity S minus 1 this time. So this time the capacity is smaller, and so we get a different kind of path space. And it turns out that in the matching complexes that are relevant for this path space are exactly these S equal partition lattices that were studied by Bjorner and Welker, and one can compute their homology explicitly and therefore get a somewhat cumbersome expression for this, for the homology of the path space. One can also look at binary path spaces, which are actually turn out to be objects that had been studied before. And these are, if you have still an arbitrary f, hypergraphing 2 to the n, you can remove from Rn all points where yi1 equals to yil, where I1 to il is a member of the hypergraph. And then the general formula simplifies as follows. And actually, this actually can also be obtained by an old result of Gorewski and McPherson, a very famous result from '88 that computes the homology of subspace complements in general. So in this case, we get exactly the same formula as their result. How much time do I have? A few minutes? Yeah.
7:43.
7:43. Yeah, maybe. Okay. Let me say that the first step in the proof is to actually translate
The proof of what?
the proof of the formula that we had is to translate the problem. Well, after all, we said that.
Sorry, you had many formulas.
Okay, so this formula. Okay. This formula. So the first step in the proof of the formula is actually to find a homotopy model for this, which is in a sense finite, which is which can be handled. And indeed, it turns out that you can describe this path space as a subspace arrangement, but not in the usual sense, but rather as a subspace arrangement in a product of simplices. And while the usual methodology of handling path spaces, in handling a plane arrangement does not work here, one can somehow modify it so it will work for subspace arrangements in a product of simplices. And so once you get a model of this space in a product of a subspace arrangement in a product of simplices, you can apply more or less standard technology of topological combinatorics and get this formula. Yeah, so you have 5 minutes. Okay, yeah, I'm done. Yeah.
Explain the connected components being relevant, but not the Betty numbers, other Betty numbers.
Why they're not?
They might be. Is there any reason they might be relevant in this programming problem?
Yeah. So I think that in a sense they want. They're not. What they want are schedules that are that the concurrency community. So I cannot speak for them, of course, but what I'm told is that they are interested in actually simple protocols. So the main thing is that it will be simple and implementable. So for example, they would like something that will go, say, on the, if you can do it on the axis, that would be very simple. But you cannot always do it. That's the problem. And so as a second best, they would want something in that moduli space of curves they want something that is kind of the simplest. So when they look for that, then apparently the general moduli space is relevant. But so that's why I said, because that higher dimensions, it's not clear that they are important, but anyway they are interesting.
Are they the notions of simplicity or complexity that you could ask, okay, finally the simplest. So just to, again, let's come back to the question I asked you before. One possibility is always player one steps, then he finishes his business, player two goes, and so on. Right?
Yeah, but that's
very simple. So
not.
Why is this not good for them? They want, presumably they want other...
For one thing...
But then they're not working simultaneously. A lot of these... you can be...
well, this is...
using processor
This is something that they don't want...
There are other criteria for the goodness of scheduling.
Yeah, so unfortunately I'm not in a position to answer, but I know that Martin actually cooperates with the guys in Paris, and they actually run programs. And actually they try to run, for example, even in Martin's example of, say, 8 points, they try to run to find the homology using Martin algorithm, and they got stuck because it's...
But if they find the homology, will that help them design a protocol?
Apparently, yeah. Apparently they are interested in that.
Can you describe this explicitly in final terms? This path space which you can
What?
the
The homotopy?
this is what you call Z.
Z. Yeah.
Do you have a finite model describing this space?
We have...
Nerve of some covering?
No. It's not a nerve of some covering. It's a so let me describe it here. Okay. Yeah. So it's df. It's this df, which has finite description. df itself is the complement in this space. This space is some Sn. This is some sphere. You remove from this. This is a sphere which is a product, which is a compactification of a product of open simplices. Okay, so if you take open simplices, you take the product, and you take compactification, 1 point compactification, you get a sphere. From this sphere, you remove something. This something is a plane arrangement in the product of the simplices. So so it's a plane arrangement here.
Maybe because this is a bit specialized, maybe it's more efficient.
Yeah. So the answer is that yes, there is a homotopy description of this.
Actually, I have a question to both of you. Is there any connection to these robotics question, configuration spaces? At least to in one expert, they sound a little similar. No?
There is an expert here. So. Okay, thank you.
Well, thank you, Roy.